Welcome to qnawire.
Here we're going to find the tension in a cable supporting a strut based on the weight hanging from its end, and also the compression force on the strut. And we're going to do this in 3 ways, but before we start off, I do want to point out that there is an assumption that the strut has negligible weight. Okay, so I'll just make a note of that. Strut with negligible weight, and that's kind of the key. And we'll say why in a little bit. So the impact of that is that if you look at the sum of the torques on the strut using the connection point, we'll call that C, as the pivot, then there are 2 forces that are creating the torque. There is the tension acting in a counterclockwise sense times sine of theta times the length of the strut. We'll call that length L is the 24 feet. And that has to be balanced by the 100 newtons. The weight at sine of 90, which is 1 times the length. So both of those forces are occurring at the length, which means that the tension sine of theta has got to equal 100 newtons. So that is going to simplify the problem quite a bit. What this means then is that the force at point C has to point straight along the strut. So let me make a quick vector diagram showing the forces on that strut. So there's the tension in the rope pulling it to the left. And there is the weight downwards and the strut force at point C. We'll call that FC. Has to point straight along the strut to cancel the X component of the tension. And in fact, let me make that a little more realistic. It has to basically cancel the X component of the tension. Okay, and this will become clearer as we work out the graphical technique. So we'll solve graphically. And I may not do a very good job here. I don't have quite a measuring tool that I could use on the screen that's very reliable. But at least it'll give us a picture of what's going on. And that's always a good idea, is to develop a picture of what's going on. So we're going to draw the weight force. And I'm going to come up with a scale here. 100 newtons, we are going to say, is 2 squares. Let me draw that as a straight line. Yes, I do have a straight line tool with a vector. So that's pointing straight down. And we'll use 2 squares. Now, the tension has to connect back up to the horizontal after moving, let's see, 10 feet up, which would be 2 squares up, and that'd be 24 feet over. That would be, let's see, 10 feet, 20 feet, approximately there. So my tension has to connect back up to the horizontal. So we'll show the tension connecting in that way. And I'll do tip to tail drawing. And that means my force compression has to get us back to 0, so we have to make a full loop. So let's see if we can do that. And let's see, can we put an arrow on that? Well, let's put an arrow on that manually. So that is the compressive force. And if we make a measurement there, we see that the compressive force is exactly what it takes to get over there. So if 2 squares down is 100 newtons, then we can make like a little ratio. 1, 2, 3, 4. 4.4 squares is to force compressive, as 2 squares is to 100 newtons. That's a little bit more, 4.8. And so we can solve for the compressive force is basically 240 newtons. Okay, now the tension, we would have to measure along the diagonal. This is where my thing is a little bit unreliable. But basically, it is about 200, let's see. Yeah, I don't have a very good ruler here. But I'm getting it about 260 newtons, which makes some sense because we can correspond it to the hypotenuse as 26 feet. So this should be 260 newtons. Okay, so we have our compressive force and we have our tension from this little picture, and it kind of helps us see what's going on. Now, graphically, there's a couple ways to do this, but basically what we see is not graphically, but from the triangle. So the triangle that we're going to focus on is, of course, the main triangle with the bottom along the strut. I'll just kind of show it schematically. And basically then we have that T cosine theta has to equal the force of the compression. Okay, so T cosine theta. And T sine of theta is equal to 100 newtons. And from the drawing, the cosine of theta is 24 over 126, the hypotenuse. And the sine of theta is the 10 over the 26. So we can basically work with those two equations and come up with both the tension and the force of the compression. The tension is 26 times 100 over 10. or 260 newtons. And that then tells us that 260 times 24/26 is the compressive force, and that's 240 newtons. Okay, now it's not much different to go from the triangle to the components. So there we're going to be using that equilibrium is such that the sum of the x components of the forces have to add up to 0, and the sum of the y components have to add up to 0. Our x components are tx is in the negative direction, and our compressive force from the left end is in the positive x direction. And then in the y direction, we have ty up and the weight downwards. So we have ty is equal to 100 newtons. And tx, of course, is going to be found from ty. So we could do some more trigonometry, but we know that ty over tx is equal to the tangent of the angle, and that's the same as 10/24. Okay, so we can solve for tx. It's 24/10 when we cross multiply times 100 newtons, or 240 newtons. So again, we find that Fc is 240 newtons. No big surprise there. It's all in the x direction, and we could just write the tension in terms of its components as 240 newtons and 100 newtons, or we can convert that into magnitude direction form. The magnitude of the tension is 240 squared plus 100 squared with a square root, and that is 260 newtons. And its angle, if we wanted to actually find that angle in degrees, we could say that tangent of theta is 10/24. Take the arctangent and we would get 22.6 degrees. And I'll just show that angle, but it's the angle in the triangle. This angle here. Oops.